Hello, my name is John Dowling. I'm the Sustainability Manager with the British Constructional Steelwork Association, and I'll be speaking to you today about design of steel-framed buildings for fire. This presentation has 5 broad themes. First of all, meeting regulations. Then I will talk about structural fire protection methods. I will then talk about fire testing. Then I'll describe the special issue of single-storey construction in fire. And lastly, I'll talk about fire engineering. Now, the first thing to say is that real fires in real buildings are very rare. This is a fire in a building in Basingstoke. The fire started on the 8th floor, completely gutted the 8th floor, completely gutted the 9th floor, badly damaged the 10th floor before the fire brigade got on top of it. In total, between start and finish, it took the fire brigade 4 hours to get on top of this fire and put it out. This is the inside of the building after the fire. Although the damage is extensive, one can see that the beams and columns have suffered no damage. In fact, the building suffered no structural damage, even though the fire lasted for 4 hours and the structure was protected to achieve 90 minutes fire resistance. This tends to support the view that some of our fire precautions may be more onerous than are required given the risk involved. If the building was constructed today, it would require 120 minutes plus a sprinkler system. The requirements for provision of fire safety in buildings in the UK is outlined in the building regulations. The regulations are couched in functional terms. In other words, they will tell you what to do, but not how to do it. There are many regulations. This one in front of you is taken from the building regulations for England and Wales and governs the requirement for structural stability. It does not, however, provide assistance on what a reasonable period is considered to be. In England and Wales, the government produces approved document B to provide guidance on how the requirements of the building regulations with regard to fire safety can be met. The fire precautions in the great majority of buildings in England and Wales are designed according to this guidance. The approved document is not a deemed to satisfy document. Its status is that, should a contravention be alleged, the use of the document will be taken as evidence that the requirements of the building regulations have been met. It is not necessary to use this guidance if it can be shown that the requirements of the building regulations can be met in another way. Fire precautions in approved document B vary according to the occupancy and the height of the buildings, and requirements change at 5, 18 and 30 metres. Most non-residential multi-storey buildings are offices, shops and commercial buildings. Most are under 18 metres in height. Therefore, the majority, about 2/3 by floor area, of multi-storey buildings in England and Wales are captured in the blue box and require 60 minutes fire resistance. One point in particular to notice is that sprinklers are mandatory in buildings over 30 metres. These must be life safety systems and be installed to specified British standards. Also, the figures in red can be reduced by 30 minutes if there is a life safety sprinkler system installed in the building. The building height is measured as shown. In fact, the height is the maximum height for access for the fire brigade. This means that most buildings under 5 metres in height, which was a special category in the table shown on the previous slide, are 2-storey buildings. Scotland has its own regulatory system for fire. These are interpreted through Technical Handbook 2. Fire resistance requirements are either short, 30 minutes, medium, 60 minutes, or long, 120 minutes. Buildings over 18 metres in height in Scotland require 120 minutes fire resistance, a height at which most buildings elsewhere in the UK require 60 or 90 minutes fire resistance. 120 minutes fire resistance is introduced in most of the UK at 30 metres. Northern Ireland also has its own system, which is very similar to that of England and Wales. With a small number of exceptions, sprinklers are not mandatory in Scotland. The provisions of approved document B have proven themselves over time, but it is recognised that it may not necessarily provide the optimum answer in all buildings. Our improved knowledge on fire behaviour has made it clear that there is room for an approach which allows designers the opportunity to specify fire precautions according to the particular circumstances of the building. This led in 2008 to the publication of BS 9999, of which the British Standards Institute said that it promotes a more flexible approach to fire safety design through the use of structured risk-based design where designers can take account of varying human factors. BS 9999 has been written as an alternative to Approved Document B in England and Wales. In Scotland, it appears that it would be looked on as an engineered solution, which would be assessed then in that way. We'll come to engineered solutions later. BS 9999 is a risk-based standard. Structural fire precautions are based on an understanding of the 4 key parameters which create risk in fire. These are building height, familiarity of occupants with the building, whether occupants are asleep, and the degree of mobility of the occupants. Of these 4, it is the middle 2 which are by far and away the most important. Familiarity of occupants with the building, whether occupants are asleep. The vast majority of people who get killed or injured in fires in buildings do so when they are asleep, and they do so in their own homes. That is what the big risk factor is. The degree of mobility of the occupants is also very important. When one looks at the World Trade Center collapses, there were 3 categories of people in that collapse who died. There were those at or above the point of impact. There were those people who went into the buildings to try and save the occupants, the rescue services. But what is often forgotten is that almost everybody in those buildings who had a mobility impairment also died. So a degree of mobility is also very important, especially in modern buildings. Also important in creating risk in fire is what the fire load is going to be in the building, the compartment size, and the presence or otherwise of sprinklers. And all of these are taken into account in BS 9999. 9999 also recognises that very tall buildings have special risks in fire, and it has introduced a new height category of 60 metres. This compares with 30 metres in England and Wales and 18 metres in Scotland as the maximum heights. This slide shows the comparisons between the structural fire resistance requirements for some common building occupancies. There's a lot of information here, but the overall lesson is that generally structural fire resistance requirements are lower in BS 9999 than in the approved document. BS 9999 has a much wider scope than just structural fire precautions, of course, and in general it provides capacity for more cost-effective solutions. One word of caution, however, is that the recommendations of BS 9999 must be applied as an entire package. Favourable aspects of the guidance cannot be cherry-picked. And if you look there, you'll see, as an example, an open plan office building over 30 metres in height with less than 60 metres in height. Approved document B would require 120 minutes plus a sprinkler system. And the same building in 9999 with a sprinkler system would require 60 minutes fire resistance. I'm going to talk now a little bit about structural fire protection methods. Structural fire protection in the UK is dominated by 3 different systems. The first and most popular are thin film intumescent coatings. The second are bore protection systems, and the third is spray protection systems. And I'll go through these one at a time. Thin film intumescent coatings are paint-like materials which react at high temperatures to form an insulative char around the steel. I have used the words thin film quite deliberately when describing this material, as thick film intumescent coatings are also available. Those have been developed for offshore and petrochemical use, but in recent years a number of manufacturers have modified their products for use in buildings. However, it is a minority product, and it is thin film coatings which dominate the market. Intumescent coatings can be decorative or non-decorative. Decorative coatings carry a significant cost premium and should only be specified where necessary. Over the past decade, thin film intumescent coatings have come to dominate the structural fire protection industry, in part at least because of the development of a successful off-site application industry. One quick point to note about this photograph is that it is a cellular beam. Because the failure mechanism of these beams differs from that of unperforated sections, a protocol exists for testing and assessment of thin film intumescents which are used on them. Only coatings which have been tested to this protocol should be used on cellular beams. As I have said, there is an active and thriving off-site application industry for thin film intumescent coatings in the UK. Fire protection applied off-site using thin film intumescent coatings is usually done in large sheds with good air movement, after which it is allowed to dry before moving it to site. This is a very successful process, but it's not the solution to every project, and it is a premium process. However, it has advantages such as clearing the critical path, taking trades off-site, making service installation easier, and removing weather dependency. Where these factors stack up, it offers considerable value. The Association for Specialist Fire Protection publishes a code of practice on off-site application. Smaller off-site application industries also exist for concrete encasement and thick film intumescent coatings. Boards offer the specifier a clean, boxed appearance and have the additional advantages that application is a dry trade and may not have significant impacts on other activities. Also, boards are factory manufactured and thicknesses can be guaranteed. Furthermore, boards can be applied on unpainted steelwork. There are broadly two families of board protection, lightweight and heavyweight. Lightweight boards are typically about 150 to 250 kilograms per meter cubed and are usually not suitable for decorative finishes. They are typically used where aesthetics are not important and are cheaper than heavyweight equivalents. Heavyweight boards are usually in the range 700 to 950 kilograms per meter cubed and will generally accept decorative finishes. They are typically used where aesthetics are important. Sprays have the advantages that they can be used to cover complex shapes and details, and also that costs do not increase significantly with increases in protection thickness and fire resistance time. This is because much of the cost of application is in the labour and equipment, and a minority is the cost of the material. Some materials can also be used in external and hydrocarbon applications. Sprays are not usually suitable for aesthetic purposes. Also, application is a wet trade and this may have impacts on other site operations. If specifying sprays, allowance may have to be made for costing for the possible requirements for prevention of overspray. Flexible blanket systems are also sometimes used. Like sprays, these can cover complex shapes but without the potential difficulties of overspray. They are a niche product with a relatively small number of manufacturers. We are fortunate in the UK in having a competitive and innovative structural fire protection sector. This has driven efficiency up and costs down to the point where the cost of fire protection is a fraction in real terms of what it was 20 or even 10 years ago. This slide gives an indication of the development of structural fire protection costs over the past 15 years. And this slide provides an indication of the changing face of structural fire protection over the past 2 decades. This period has seen a steady increase in the dominance of thin film intumescent coatings with a matching decline in other methods, most notably sprays. One doesn't have to use those proprietorial methods, of course. There are lots of other ways of achieving structural fire resistance as well. Concrete encasement is still used occasionally, in particular where resistance to knocking, damage and abrasion is important, such as the example you see here, which is in an underground car park. Block filling of columns can provide up to 30 minutes fire resistance, and slim floor and slim deck can provide up to 60 minutes fire resistance without any fire protection. And these, in particular, are an illustration of methods of building the fire resistance into the structure, which obviously has very distinct advantages. This can also be illustrated by the, it must be said, rarely used method of shelf angle floor beams, which can also achieve up to 60 minutes inherent fire resistance without protection. High periods of fire resistance can also be achieved by reinforced columns and beams of the type shown here. The design method for this form of construction are included in EC4 Part 1.2, but it is expensive and unlikely to find wide acceptance. And of course, hollow sections with reinforced concrete can also achieve considerable levels of inherent fire resistance. I'm going to move on now to talk about testing. Much of the preceding information has made reference to 60 or 90 or 120 minutes fire resistance. What does this mean? Does it mean that after a fire in a building has lasted for 60 minutes, the building will collapse if it has 60 minutes fire resistance? The answer to that question is almost certainly no. It means that if a single loaded element of structure from that building is tested in a standard fire test for 60 minutes in an accredited laboratory, it will fail. However, a standard fire test bears little relation to a real fire, and in practice it is almost certainly much more severe. You can see the time-temperature relationship for the standard fire test in the graph shown here on the left, which shows a steadily increasing temperature over time. In practice, this will never happen, because a fire can only last as long as there is a fire load in the building to burn. Once that is burned, it will go into decline. So, if a steel building is subjected to a fire for 60 minutes, and it is fire protected to achieve 60 minutes fire resistance, it is unlikely to fail. We'll come back to this again later. The photographs on the right of the screen are, on the top, a typical scene from a fire test from the top of the furnace, and on the bottom is a view inside the furnace on a spray protected beam. Changing the subject again now, I want to spend a little time on single-storey buildings. Generally speaking, fire precautions in the UK as set out in documents such as Approved Document B exist to protect life. That they have a property protection function also is a happy coincidence. Single-storey buildings in fire are not generally considered to create a significant risk to life, and so are generally left unprotected. Section 7.4 of the approved document excludes from the definition of elements of structure that which only supports a roof. This exclusion means that structural fire protection is not required. Exceptions may occur where an element of structure provides support or stability to elements such as a separating wall, a compartment wall or the enclosing structure of a protected zone, an external wall which must retain stability to prevent fire spread to adjacent buildings, or a support to a gallery or a roof which also forms the function of a floor, for example a car park or a means of escape. It is the third of these four, that is, an external wall which must retain stability to prevent fire spread to adjacent buildings, which is the most common, and it is generally called a boundary condition. Where single-storey buildings collapse in a fire, there is a danger that the collapsing roof structure will pull the perimeter stanchions down and allow the fire to affect adjoining buildings. This is the boundary condition. Where a boundary condition exists, the designer has the choice between protecting the whole building or using the Steel Construction Institute guidance, single-storey steel-framed buildings and fire boundary conditions. This outlines a method of designing the stanchions on the affected wall so that they will stay upright and support the affected wall while the remainder of the building is allowed to collapse. It includes details of how to deal with non-portal frames, buildings with internal floors, buildings with internal compartmentation, and buildings supporting lean-to sheds. The key issue with single-storey buildings and boundary conditions is to avoid fire protecting the whole building by ensuring that the walls on the affected boundary remain standing in fire. This can be done by designing the base of the stanchion to resist the overturning moment caused by collapse of the unprotected rafters. Generally, this may require that square bases become rectangular in shape on plan, and a greater number of large holding down bolts are required on the outer edge. The base plate may also be thicker or perhaps unstiffened. There are limitations on the size of buildings on which this method can be used, and where these are exceeded, it is recommended that a fire engineered solution is sought. Where the buildings are fitted with sprinklers, advice is provided in the SCI publication as to whether or not it is necessary to design the stanchions to resist the overturning moment. And if this design method is used correctly, this is what the building will look like after the fire. The walls have been cleaned, but it can be seen that the stanchions have remained upright. I'm going to move now to the subject of fire engineering. We have already seen that one does not have to use the approved document B to develop a fire strategy for a building in England and Wales. In fact, the quote given here states that for certain buildings, a fire engineered approach may be the only way to ensure that the building is safe in fire, and this quote is taken from approved document B. Fire engineering is generally applied to large and complex developments, although it has wide application also in finding solutions to particular problems in the design of fire precautions. The Institution of Structural Engineers supports the use of fire engineering. The most up-to-date version of this publication dates from 2007, but it remains an excellent introduction to the subject of fire engineering. And critically, it says that by adopting a performance-based approach to structural fire engineering, more economic designs can be achieved and more innovative and complex buildings can be constructed. Before going into the subject of fire engineering, I want to revisit a point that I made earlier about the severity of real fires compared to the standard fire test. The standard fire test curve is shown in red. The green curve represents a typical real office fire in terms of the temperatures to which any particular element of the structure is exposed. It can be seen that it is much less severe than a standard fire test. This explains why the Basingstoke building, shown right at the start of this presentation, was able to survive a 4-hour fire with only 90 minutes fire resistance. It is because the fire was only at its most severe at a given point within the building for a limited period. This also tells us that many fire precautions in buildings may be overspecified, and if we can predict the temperatures within a fire compartment, we will be better able to match the fire precautions to the risk. And we can do that. There is not the time within this presentation to explain how this works in detail, but it is now possible to calculate how severe a fire in a compartment will be compared to a standard fire test. This involves calculation of time equivalent. Where, for example, one calculates that the time equivalent of a compartment fire was 40 minutes, this means that a fire in that compartment would be as severe as exposure to the standard fire for 40 minutes. Sports stadia are an excellent example of where fire engineering can bring value. From the approved document, most require 90 minutes fire resistance, but engineering assessments usually show that this level of protection is only required in isolated areas and that varying periods are required elsewhere. Steelwork in concourse areas is usually unprotected due to the relatively low fire load. A more recent example is Maxim Office Park, which we can see here. This is Eurocentral outside Glasgow, where time equivalent calculations enabled the engineer to demonstrate that a general reduction in fire resistance periods from 120 to 60 minutes could be justified. In total, there were 10 buildings, and from Scotland's Technical Handbook 2, because each building was a single compartment of more than 4,000 square metres, the fire resistance requirement was 120 minutes. The engineers calculated that at the time equivalent of the buildings, the severity of the fire compared to the standard fire test was just short of 30 minutes, sometime between 26 and 28 minutes. A significant degree of conservatism was introduced into the calculations by making assumptions as to unfavourable variations in certain parameters. For example, ventilation conditions were changed to reflect the most onerous conditions. These might occur, for example, if all the windows did not break. In the end, reductions in fire ratings to 60 minutes were accepted in 9 of the buildings and 90 minutes in one of the buildings. The previous slides demonstrated fire engineering as it is applied to obtaining reductions in fire ratings in buildings. This has the effect of reducing the overall cost of fire precautions. I'm now going to move on to structural fire engineering. Modern structural fire engineering dates back to a series of fire tests carried out between 1994 and 2003 by the Building Research Establishment and the then British Steel, now Tata Steel, on a composite steel deck building at Cardington. The genesis of these tests was a large-scale fire which took place at the Broadgate Phase 8 development in London in 1990. The building was under construction and was only partially protected. The fire was severe, and according to all that was known at that time about real structural behaviour in fire, which was based on the standard fire test and isolated elements of structure, this building should have collapsed. An investigation concluded that the reason it did not collapse was that the composite steel deck floor somehow developed considerable inherent strength in fire via a mechanism which was not then understood. This told us that these buildings behave much better in fire than was apparent from the standard fire test. The question was, how could the industry make use of this added strength and how did it occur? Incidentally, despite the apparent damage in this photograph, the structural repair was less than 5% of the total fire loss. The largest contributor to the costs of the fire was the cladding, which had to be replaced almost in its entirety due to intensive smoke damage. This led in 1994 to the Cardington Frame, an 8-storey composite steel deck building near Bedford. For 3 years between 1994 and 1997, Tata Steel, then British Steel, and the Building Research Establishment attempted to burn down this building via a series of 6 tests. A 7th test was carried out in 2003. The fires were intense and severe. Several of the tests attempted to replicate the standard fire test for 60 minutes. This was achieved, but it was difficult, and demonstrated again that real fires are unlikely in practice to be as severe as the standard fire test. The test data on the Tata Steel tests can be found at the Fire One-Stop Shop on the internet. We'll come to that again in the final slide in this presentation. The fire load was provided by gas, wood, or in this, the most severe of all the fires, office furniture. In all the tests, the beams were unprotected, and that can clearly be seen in this photograph. The purpose of the tests was to demonstrate that composite steel deck floors had much greater levels of inherent fire resistance than was apparent from fire tests on individual members, and also to try to understand the mechanism by which this occurs so that it could be utilised in design. This is a short video of one of the fire tests. It is the office fire. To get the temperature to the level at which we wanted, we included some wood and plastic in the compartment. This is the fire a few minutes after ignition. We wanted to get the maximum temperatures to the levels which would be found in a standard fire test. In this case, these were about 1100 to 1200 degrees centigrade. This meant that we needed to introduce or induce a flashover condition. This is characterized by spontaneous combustion within the compartment. There are a number of different forms of flashover, and it often occurs when temperatures at ceiling level reach about 600 degrees centigrade. You are looking here at a post-flashover condition. The temperatures in the middle of the compartment at this point are about 1200 degrees centigrade. This is about 450 degrees centigrade higher than the maximum temperature which occurred in the fire at Basingstoke, which we saw at the start of this presentation. And here you're looking at the aftermath. We are looking at beams which are bent and distorted, but on which there has been no collapse. This is the aftermath of the office fire test when everything had been cleared up. The beams deflected significantly, about 1100 millimeters on a 9.5 meter span at the maximum, and this retracted to about 700 millimeters on cooling. But the floors remained intact. The beam survived a temperature of 1100 degrees centigrade. A standard isolated beam of this size in a fire test loaded to the same level as the Cardington frame would have failed at about 700 degrees centigrade. So what did the tests prove? They proved a number of things. The first thing they proved was that composite steel deck construction has significantly greater reserves and strength than is indicated by tests in individual members. It proved also that columns are critical stabilising elements and must be protected. We know this because in one of the tests we didn't protect the column to full height and the top unprotected part buckled. It also told us that not all beams supporting composite steel deck floors need to be fire protected in order to prevent structural collapse and fire. The tests also enabled us to understand the mechanism by which the composite steel deck floors generate so much more capacity than is apparent from small standard fire tests. I won't go into the detail, but analysis of the test results has shown that the load path mechanisms of a steel structure supporting a composite steel floor during a fire are different from those assumed during the normal use of the building. In particular, membrane action of the slab at large displacements enables it to enhance its load carrying capacity, and this enhanced capacity is what provides the additional capability. For those who are interested in pursuing this further, details can be found in a number of sources, one of which is BRE Digest 462. The mechanism is sometimes called the Bailey method, after the person who first developed it. The Steel Construction Institute has developed a spreadsheet calculation method which uses the Bailey method for design of hot-rolled structural steel with composite steel deck floors. This can be downloaded free from the internet. It is restricted to rectangular grids only and provides a simple pass-fail answer. An alternative is Vulcan Light, developed by the University of Sheffield. This is based on sophisticated finite element analysis and uses the full engine of a much larger program called Vulcan. It provides comprehensive outputs including deflections, temperature time curves, member forces, slab cracking and animated representations of the deformation history. It is not a simple pass-fail assessment like T-Slab. It is a proprietary program for which a fee is charged. Using T-Slab and or Vulcan Light is within the capability of most structural engineers. Where these programs are used, they can produce designs such as we see here, with most secondary beams unprotected. It should be noted that some compensating features may be required. The most likely of these is that the mesh may be increased in size over that required for normal cold design. This is because it has been discovered that the mesh is a critical element in developing the enhanced capacity of the slab in fire. Also, when using these methods, careful placement of the mesh on site is required. I'm now going to discuss large-scale structural fire engineering as it applies to whole floors and frames and steel-framed composite buildings with composite steel deck floors. The ability to carry out the type of analysis I'm going to describe here is restricted to a relatively small number of specialist consultancies. Fortunately, most of these are in the UK, and this is an area in which this country leads the world. I have taken as my example a project called Ropemaker Place, and I would like to acknowledge the support of Arab Fire in this. The details of the building, a large London office, are shown. 21 stories, 3 levels of basement, approximately 84,000 square metres of floor area in total. Details of the floor design are shown. It's a fairly standard steel frame with long span cellular beams, a composite steel deck floor and concrete cores. An analysis of this type has an overarching strategy. It needs to examine the structural behaviour in a realistic fire. It needs to look to develop a performance-based fire protection strategy. It needs to demonstrate that the stability and the compartmentation are maintained in the structure. It needs to look for weaknesses and modify the structural design if required. And it also needs to demonstrate that the final solution is a robust solution. What Arab Fire sought to do on this project was to demonstrate that the secondary beams could be left unprotected whilst relying on tensile membrane action in the slab. This, to remind you, is the mechanism that enabled the Cardington frame to survive. The aim was to protect those beams shown in red and leave the remainder unprotected. It is worth noting that the fire resistance period for the structural frame was 90 minutes. One would conclude, therefore, that Arab Fire had been successful in obtaining a reduction as approved document B, and some relevant local requirements would have called for 120 minutes. The analysis had 3 stages. First of all, calculate the characteristics of the real fire in that building and its associated temperatures. Secondly, calculate the heat transfer from that fire to the structural elements, and once that was done, calculate the mechanical response of the structure to the seat in terms of deflections, strains, forces, alternative load paths, etc. This shows a plan of the floor with the fire protection marked in red. It is usually not possible to remove this much fire protection from a structural frame without putting in some compensating features. In this case, there were two. Firstly, additional loose rebar above the midspan of the secondary beams supporting the 13.5 metre bays was necessary because of the increased hugging moments in that region due to the high deflections of the slab. Secondly, because the unprotected secondary beams will deflect considerably in a fire, it was necessary to ensure that the connections had sufficient flexibility to absorb the additional movement. This was done by the use of ductile end plates for the secondary beam connections. And this is what one of these buildings looks like before the suspended ceiling is installed. And finally, this is the opening page of the one-stop shop which I mentioned previously. This contains all the information on all materials in fire, or the great majority of structural materials. It is backed by Tata Steel, amongst others, and developed by the University of Manchester. Included on this site is all the data from the Cardington tests, as I mentioned previously. If you want to know anything about fire, or you're looking for any information, this is an excellent source. And that's the end of the presentation. Thank you for listening.